Hi, in this video we're going to continue our discussion of chapter 15.1, all about multiple integrals over rectangles. So, in the last video we discussed the theory. It all amounts to, for f of xy, the volume under the surface over a region R. Usually it's going to be rectangular in this video. In the next section, we'll talk about, again, general shapes, is given by the volume equals a double integral over a region R, f of xy giving the heights, dA giving the area of one of the infinitely small sub-rectangles we're using, where dA equals dx times dy, or dA equals dy times dx. So if R is rectangular, then R is equal to some interval in X region times some interval in the Y region, right? Or we could write it in our set builder notation. It's all of the points X, Y, such that X is between A and B, and Y is between C and D. That's literally what a rectangle would be. We're binding the X by constants, we're binding the Y by constants. And our volume can be written as either the integral from C to D, then we're going to do the integral from A to B. Sorry, it's actually the opposite order. F, X, Y, and then it would be dx first, then dy. So let me say that again more clearly. We're going to have an integral in the x direction first, treating y as a constant, and then we're going to do this integral of that. So if we're treating y as a constant here, that means there'll still be y variables left after we evaluate and substitute in our x values. What's surprising is that this is also equal to if you wanted to do it in the other order, meaning y first, going inside to outside, and then x. So this is the y first. That's how you have to keep track. It's going from the inside out. So this is y first, then x, y first, then x. This is x first, then y. It might be surprising to you, but it should make sense based on what kind of a region a rectangle is, that these two are the same. We're not going to prove this theorem, but this is our first version of Fubini's theorem, which is a fun name to say, Fubini's theorem. That these two rectangular integrals are the same no matter what order you do it. We'll prove that with an example. Let's say evaluate this double integral over the rectangular region R, x squared y dA. So notice that that is a double integral because we haven't specified the order of integration. We haven't iterated it. We haven't written it as two integrals yet. It's kind of like a double integral symbol. Two integrals really close to each other in some textbooks. Over R equals, and here's how we can write this rectangle one more time. So we're going to have the x's go from 0 to 3, and the y's go from 1 to 2. There's two ways to do such an integral. A, we can break it up into a x first, then y. So we do y second, y should be on the outside, x on the inside. And then again, make sure you're understanding it's dx and then dy. So just to be clear here, it's just like I'm going to do this integral first. When I do this integral, I'm going to treat y like a constant. It might help you, just like when we first started doing derivatives, to imagine that y is a number. What if this integral were 5x squared? You would just use the power rule. And we'd have, keep the integral on the outside. We'd have add 1 to the power, multiply by the reciprocal, and plug in these values. Now, for when we're doing this, I often seen students get confused about what you're plugging in. It might help you to write down this is from x equals 0 to x equals 3. And then this is all still stuck inside an integral with respect to y. When I plug in 3, I'm getting 27 times 1/3, or 9y, minus 0. And so really all we're left with is a Calc 1 problem. If you do this right, this should only have y's and constants in there. If you've done the integral correctly, there should not be x's anymore because you've evaluated all the x's in this step. And now we're just going to get 9/2 y squared, evaluated from 1 to 2, which is 36 over 2 minus 9 over 2, or 27 over 2. Now, kind of proving Fubini's theorem for this problem, we're not usually going to do the problem twice in 2 different ways. I'm just showing that it works and getting you guys used to the idea that you can reverse the order, especially for rectangles. Hint, hint, hint. X squared y, it would change if I changed that variable. And now again, notice in this red version of the problem, we are doing y first. And you can notice that because y is on the inside, then x. So again, we're just focusing our attention on this inside integral. This says integrate y, treat x like a constant. Well, if I'm supposed to be treating x like a constant, I'm going to just add 1 to y's power, leave the x alone, and multiply by the reciprocal of y's power. Evaluate, and again, I recommend writing down what you just did. It was y equals 1 to y equals 2. So you know where you're plugging in those 1 and those 2. 0 to 3. I'm going to get, plugging in y as 2, 4x squared over 2. I know that could simplify, but I'm going to subtract by 1 over 2 x squared, or x squared over 2. I guess I could have written it like that. And that's 3 over 2 x squared. And now again, we're left with a Calc 1 problem, and we can easily go, add 1 to the power, multiply by the reciprocal, you'll just be left with 1/2, and that's going to be 27 over 2. You shouldn't feel the need to do a problem both ways. You should just trust that it works. Really, do it the way that makes sense. That'll be another caution. So let's give you another one to try for yourselves. So again, this is technically a double integral. It is not iterated until you break it up the way you would want, where r equals, again, let's do x, y's, where 0 is less than x, less than or equal to 1, and -1 less than or equal to y, less than or equal to 2. I want you to try this problem out. I'm going to say I'm going to do the x's first. So I want you to try to set up your iterated integral with x's first. Try to fill in the bounds and try to do x's first. It doesn't matter to do x or y first here. I'm just trying to say that so that way you can follow along with my work. Pause video right now and try it out. 3, 2, 1. Okay. So if I do x's first, I should have 0 to 1 here and negative 1 to 2 here. So we're going to treat the y like a constant. So if the y were a constant, it would say something like plus 25. If I'm trying to integrate x 25, I can do 1/2 x squared plus, it would be 25x. But sometimes we'll write the x in the front, okay? Again, I'm saying this guy, easy to integrate with respect to x. This guy, treat it like it says 25. Treat it like it says 49. Like any constant, it would become that constant times x. And again, the reason it's being treated like a constant is just like when we did derivatives. This says treat the x like the variable, treat y like a constant. And we're evaluating this from 0 to 1. This is a good choice for the order because when we're plugging in 0, a lot of stuff's going to go away. I have 1/2 plus y squared minus, they both will evaluate to 0. I hope we agree about that. Now, if I want to integrate this with respect to y, okay, so we're just going to go right back to 1D, one variable, constant times y plus 1/3 y cubed, evaluating from y equals -1 to y equals 2. So that'll be 2/2 plus 8/3 minus, parentheses, be careful, -1/2 minus 1/3. So that's me getting 3/2 plus 9/3, 9/2. Okay, another one. This is a much more interesting problem for a reason you're about to see. If we have y sine xy, where, dA, where r equals 1, 2 cross 0, pi. Okay, rectangular region in 2D space. Remember, the y is always going to come second, just like it does with the coordinates. So this is a really important example because if you look at this integrand, you might notice that if we did y first, we'd have a problem. If we did y first, we'd have a big problem here. Why is that? Y first. You'd have 1 to 2 on the outside, 0 to pi on the inside, y sine xy, dy dx, right? If we decided to do this, we would have to worry about what's going on here. And again, it's better to go back to AB land and ask yourself, how would you do this integral? Even if it was indefinite, how would you do this integral? And you can't use a calculator because it's indefinite. And we're going to pretend Wolfram Alpha doesn't exist. This would be requiring, it would require integration by parts. The x doesn't help you. The x doesn't make it easy, doesn't make it hard. It just would require integration by parts. There is no help there. Because this guy's a variable, this guy's a variable. Use substitution or just thinking about what the integral should be here. Oh, that should be like, we need a 5. We don't need a y there. So this is a bad method. So to clarify what I was saying about Fubini's theorem, it doesn't matter which order you want to. It won't change the value you get. But it does matter what order you use, because sometimes integrals will be hard or even impossible if you choose the wrong order. So in this problem, you're really seeing that we need to do the y's second. And in this class, you will always have some way of doing the problem. Sine xy, dx, dy. So again, whether you think about this as a u substitution or not, now we're really doing something much more like replacing the y's as a constant, 5 sine 5x. And now you might notice, oh, if I did u substitution, or I just thought, oh, the derivative of the inside is this 5, this is a lot more doable. This is a good integral. So we can just go right on and undo, find the antiderivative here, and get negative cosine xy from x equals 1 to x equals 2 dy. I don't want to lose anyone here. Again, use u substitution, use reverse chain rule, however you're thinking about it. The derivative of this, double check, derivative of negative cosine would be sine. Keep the inside the same. The derivative of the inside with respect to x, the derivative of the inside with respect to x is that y. That's why that y kind of hooks off. Plug in the 2 for x, plug in the 2 for y. We would get negative cosine, plug in the 2 for x, plug in the 1 for x. 2y minus a negative is a plus, cosine y dy. Integrating these guys again, we should get negative 1/2 sine 2y plus sine of y. Evaluated from 0 to pi. Plugging in pi gives me 0. Plugging in 0 also gives me 0, so it's 0. This is not something you could find by doing the red integral. The red integral will also evaluate to 0, but again, in terms of being able to do it, it's a lot harder. All right, let's get into the problems that say more of a natural kind of setup. Find the volume, it's all going to be somewhat unnatural, of the solid bounded by the paraboloid x squared plus 2y squared plus z equals 16. The planes x equals 2 and y equals 2, and the 3 coordinate planes. So if I want to go under this surface, my first goal is to turn this surface equation into a function. And just like in Calc 1, you can solve for x, solve for z, solve for the variable we're interested in, again, especially the easiest one to solve for. So z equals 16 minus x squared minus 2y squared. That's as good of a function as any. We want to make sure our function only has 2 variables. That's why we're solving for z. And if we're above the coordinate planes are where x equals 0, where y equals 0, and where z equals 0. It's exactly the situation we're talking about. And the planes x equals 2 and y equals 2. So we're talking about the coordinate planes. We're talking about x equals 0, y equals 0, and z equals 0, although that's not going to matter as much. That just means we are going to stop at the xy plane. This should be clear that we're talking about the rectangle from 0 to 2 by 0 to 2. Because we're going from where the x's are zeros to 2, the y's are zeros to 2. So we do in fact have a rectangle. So our integral would be a double integral over that region, f of xy dA. That would give me the volume they're looking for. The question is, which one do you want to do first? I really think you should just pick now. There really is no better answer. Go ahead, see what number you get. It should be a whole number. And pause the video, see how it goes. 3, 2, 1. I'm going to go for y first this time because y first last time did not work. It's going to be a little confusing, and this is why you should always label very clearly, because the x bounds are the same as the y bounds. So if I want to integrate this with respect to y first, I'm going to add y's to the constants, the people who are constants with respect to y, and use the power rule on our one y term that is actually there. Going from y equals 0 to y equals 2. Please be careful about plugging in 0. A lot of students assume you're all going to get 0, 0, 0. Do we in this case? Yes, because each of them just has a y in it. So when I plug in those 2's, I'm going to get 32 minus 2x squared minus 16 over 3 dx. Not the prettiest function, not the prettiest function. If I simplify that a bit, I will get 80 thirds minus 2x squared. Integrating this back in 1D land, 80 thirds x minus 2 thirds x cubed. Carefully plugging in the 0, carefully plugging in the 2. 160 thirds minus 16 thirds. And I think if you simplify all that, we're going to get 48. One last special example, one last special rule here. Special situation. I'm going to say special a bunch of times because I don't want you assuming this always works. If integrating over a rectangle, AB cross CD, our normal setup, and f of xy equals g of x times h of y. Okay, that means you can break up f into a function that just has x's or a function that just has y's, and a function that just has y's. So f is separable, can be factored into x stuff and constants times y stuff. It has to be times, it cannot be plus. It has to be times, it cannot be plus. It has to be times, it cannot be plus. Then the double integral over r against f of xy dA equals, you can do it as an integral from a to b of the gx function times cd of the hy function with respect to y, because they're all just constants with respect to each other. So nothing else is interesting. Now, examples, e.g. f of xy, there's lots of kinds of these, like x squared y, the first example we did. That could be separated into g of x equals x squared, h of y equals y. That's what I'm saying. Or f of xy equals x squared y plus y. Well, see how I can factor this as y times x squared plus 1. So again, that could be h of y. That's a function that just has y's in it. That's a function whose only variable is x. Okay. I could have made it like y cubed here also. It doesn't always have to be just the y's. So you never have to do this, but it can make your situation a lot faster, or at least cleaner. Such as with this example, r equals our rectangle from 0 to pi over 2, and times, let's say, 0 to pi over 3 in the y direction. And you want to integrate r sine x cosine y dA. So instead of just picking an order and switching to iterated, we can just totally decompose it or separate things into an x integral from 0 to pi over 2, because I know that's the guy who comes first, sine x dx, times an integral from 0 to pi over 3 cosine y dy. And you'll get the right answer. This only works because I can break this up with multiplication. And because I'm over a rectangular region. Things are going to get a little more interesting when we're not doing rectangulars in the next section. So, you should feel free to try this out. Pause the video now and see if you get the right answer. It is just two AB integrals, two Calc 1 integrals, so it should be straightforward. 3, 2, 1. Cosine x from x equals 0 to x equals pi over 2 times sine y from y equals 0 to y equals pi over 3. This is negative 0 plus 1 times root 3 over 2 minus 0. So overall, I'm getting root 3 over 2. Ta-da. So that's all there is to it. It's going to get a little more complicated in the next video when we're starting to do more general regions. But I hope this video made sense. Thank you for your hard work, and I'll see you in the next one. Bye.